We are going to look at partial derivative. Let z is equal f of xy be function of two independent variables x and y. The partial derivative of z with respect to x is the ordinary derivative of z with respect to x. While y is kept as constants. Now, what we are defining here is the partial derivative of any function. Let's say equal f of xy be function of two independent variables x and y. The partial derivative of z with respect to x is the ordinary derivative that we know, ordinary differentiation of z with respect to x, while y is kept constant. Now we know that if two parties, for instance, two parties are involved, they have misunderstanding and somebody wants to go in to settle the case, and that person is citing one particular party without the other. How do we put it? We will say that the person is partial in his judgment. That is what is happening to functions of several variables. We are going to differentiate partially. We are going to be partial to one variable while we are dealing with the other. Then later, we will also be partial to the other. It's very interesting to watch. So now, let me show you one simple thing. Recall that in function of one variable, suppose I have like this. In one variable, I have y is equal maybe 2x squared plus x. You see that the y, the x, which we know, will be equal to 4x plus 1. You know this. But this one involves 2. So we are not going to deal with only x, but rather we'll deal with y. Now, let's continue from where we stop. That it is denoted by partial z, partial x, or z subscript x. If I write like this, what I mean is partial z, partial x. You know, note that this one is not d, z. It's not d. See the new notation for partial. This one is for elementary calculus. We use the z, the x. But this one is partial. So when you see this, see, look at the curving of it. Partial. Alright. So it's denoted by this. Now, by definition, partial z, partial x will be equal the limits of f x plus change in x y minus f of xy all over change in x as change in x approaches 0 by definition. partial z partial x is equal to this. Now let's prove. We have z is equal f of xy. We know that by first principle from what? Elementary calculus, we know that when there is change in z, that is change in z, will be equal change in x. Now notice that change only occur in x, doesn't occur in y. So we are partial to y because y and x was here together, they were here. But I'm dealing with x as if I'm not seeing y. So I'm partial to y. So that's what you call it, partial derivative. I'm dealing with one, leaving one. Now, if we have this, still from our knowledge of first principle differentiation, I'm going to subtract z from both sides. If I do that, I will have z plus change in z minus z is equal f of x plus change in x y minus f of xy. You know why? Because z is equal f of xy. So I'm subtracting z here, and I'm subtracting f of xy. Look at z is equal f of xy. So I'm subtracting z from this way. This way also I subtract f of xy, which is equal to z. Now, if I have that, I will now get change in z, because z and z will be equal f of x plus change in x y minus f of xy. Now dividing both sides by change in x, I will have change in z over change in x will be equal x plus change in x y minus f of y over change in x, because I'm dividing through by change in x. Now taking limits as change in x approaches 0, we'll have that partial z partial x will be equal a limiting value of x plus change in x y minus f of xy over change in x as change in x approaches 0. Now look at the definition. We are able to show the definition now of partial z partial x is equal to this. Now, similarly, partial z partial y will be defined as limiting value as change in y approaches 0, f of x y plus change in y minus f of xy over change in y. Look at that. Partial z partial y is denoted by this, and it is equal to the limiting value of change in y approaches 0. Of this function as change in y approaches 0. Now let's prove this. Proof. We know that z is equal f of xy. Z is equal f of xy. And so when there is change in z, there will also be change in y. Look at that. Change in y. there is no change in x. So x is partial this way, as if x doesn't exist. You see, we share the changes to z, we share to y, but z, I mean x is there without having any change. So in that way, we can then subtract z from both sides. Then we have z plus change in z minus z will be equal x, y plus change in y minus f of xy. The same thing happened that here I subtract z, y the other side, I subtract f of xy, which is equal to z. So we have change in z will be equal f of x, y plus change in y minus f of xy, and divide both sides by change in y. If you do that, we have change in z over change in y will be equal f of x, y plus change in y minus f of xy over change in y. Now take limits. Taking limits as change in y approaches 0, we then have that partial z partial y will be equal to change in y approaches 0, f of x, y plus change in y minus f of xy all over change in y. So we are also able to prove that this is true, that this one is equal. This partial z partial y is equal to the limiting value of f of x, y plus change in y minus f of xy over change in y as change in y approaches 0. Yes. So this is how we define partial derivative. Now we are going to take some examples that will help us understand how we perform partial derivative of functions of several variables. It's very interesting. Alright. Okay, so let's take this example. If u is equal to x squared minus xy minus y minus z squared minus 5, find partial u partial x, partial u partial y, partial u partial z by first principle. So we are going to use first principle definition to evaluate this. Now let's take the solution. We have that u is equal to x squared minus xy minus z squared minus 5. Alright, so we need partial u partial x, and that would be u plus change in u will be 2x plus change in x squared minus x plus change in x y minus z squared minus 5. Notice that change only occur in x because we want to differentiate partially with respect to x. Change does not occur in y. Change does not occur in z. Now we will have u change in u will be equal to x squared plus 2x change in x plus x squared plus change in x squared minus x plus change in x y minus 6z squared minus 5. This is done by binomial expansion because x plus change in x squared means x plus change in x times x plus change in x. But by binomial expansion you have this. I just use binomial expansion approach. But if you want to times the two together, you still get this. And now binomial expansion is very important in evaluating especially first principle. If you want to differentiate a function by first principle, you must know, because if this function, maybe if this variable were to raise the power maybe 4, 5, 6, before you expand it, you must have the knowledge of binomial expansion. Now, I also advise to have lectures on binomial expansion, a special package that can teach you how you use binomial expansion to expand. Alright, so here we have 2x squared plus 4x change in x plus 2 change in x squared minus xy minus y change in x. You see, I'm multiplying this, minus z squared minus 5. So that is u plus change in u. And then we know that the next stage is to subtract. So subtract u from both sides. We do that, we'll have u plus change in u minus u will be equal 2x squared plus 4x change in x plus 2 change in x squared minus xy minus y change in x minus z squared minus 5 minus u this way, and u is 2x squared minus xy minus z squared minus 5, which, if I open this bracket, I will have minus 2x squared plus xy plus z squared minus 5, then 2x squared plus 4x change in x plus 2 change in x squared minus xy minus y change in x minus z squared minus 5. In that case, okay, we have plus 5 here because of this, opening this. So in that case, 5 can cancel here, minus 5. Then we have z squared, we have minus z squared, we can go. We have minus 2, and we have plus 2. We also have plus xy, and we have minus xy. Yes. So these are all that we have there. And then u and minus u can go. So change in u become this, which means change in u will be equal 4x change in x plus 2 change in x squared minus y change in x. Okay, that is what remains there. Now, we can also define it in this form, that from here now we have change in u is equal. Okay, the next thing is we are going to divide both sides by change in x, because what we need to define is change in x. So I'm going to divide both sides by change in x, and then I will have change in u over change in x will be equal 4x change in x yes, over change in x plus 2 change in x squared over change in x minus y change in x over change in x. That will give me change in u over change in x is equal 4x, because this can cancel this. Then plus 2 change in x, because this can cancel this, remaining 1 minus y. Now, leave the change in u, change in x as change in x approaches 0, will mean that partial u, partial x will be equal 4x plus 2 of 0 minus y. And if I have that, partial u, partial x will be equal 4x minus y. No, this is 0. So 4x minus y. So that is partial u, partial x, giving you 4x minus y. Alright. Now we can also find partial u, partial y. Now look at, let's define for partial and partial y. We have the function that u is equal to x squared minus xy minus z squared minus 5. Remember, we want to find partial u, partial y. And then from here, if we talk about increment, increment must be for u. Then x will not have increment because we are talking about y. We are differentiating with respect to y. So minus x, then we have y plus n in y minus z squared minus 5. That is only the increment is involved for the independent variable. So here we have that u plus change in y, change in u, yes, is equal to x squared minus xy minus x change in y minus z squared minus 5. Alright. Which means that we can subtract u from both sides. If you do that, we'll have u plus change in u minus u will be equal to x squared minus xy minus x change in y minus z squared minus 5 minus u. U is 2x squared minus xy minus z squared minus 5. So that means we will have 2x squared minus xy minus x change in y minus z squared minus 5 minus 2x squared plus xy plus z squared plus 5. Okay, so now we see that u plus h in u minus u is equal to this. So this and this can go, then we have change in u. In here we have 2x squared and minus 2x squared. So the two can cancel themselves. We have xy minus xy and xy. We have z squared and plus z squared. We have minus 5 and plus 5. So the thing that remains there is minus x change in y. Yes, that is what remains. Minus x change in y. Okay, now if I divide both sides by changing y, okay, I will have change in u, change in y is equal minus x change in y divided by change in y. So what I have here is that by now taking limits, if I take limits here, taking limit, we have partial u, partial y is equal minus x. So that is what we have. We have minus x after taking limits of this function as change in y approaches 0. So we have minus x. Now the same definition also applies if we will use if we want to find for z, that is partial u, partial z. U is 2x squared minus xy minus z squared minus 5. Increment occurs in u, but not in x, not even in y, but in z. We will have z plus change in z squared minus 5, which is the same as 2x squared minus xy minus z squared plus 2z plus 2z change in z plus change in z squared minus 5. So this is the expansion of this place. And this can give us 2x squared minus xy minus z squared. Look at that. Minus 2z change in z minus change in z squared minus 5, which also gives that u plus change in u is equal to 2x squared minus xy minus z squared minus 2z change in z minus z change in z squared minus 5. Okay, minus then z will give us, u give us 2x squared minus xy minus z squared minus 5. That is subtracting u from both sides. So we have change in u. See, I'm subtracting u from both sides. Will be the same as this will cancel. Okay, let me put it clear so that you will get it right. Change in z squared minus 5 plus, this place will be plus when you put on here, and then we have 2x squared plus xy minus plus z squared plus what? 5. That will give us this can cancel this, and then z squared can cancel this. We also have minus sy can cancel this. Okay, see this, but this is minus, so minus 2x squared can cancel this. So the only thing that remains is minus 2z change in z. So change in u is equal this. So taking the limits as change in z approaches 0, we have partial u, partial z. You see, we are going to divide first. Divide. If you divide through before you take the limit, if you divide, then this will go. So what remains there is minus 2z. Yes, because if you divide both sides by changing u, then we will have this change. By changing z, we divide this by changing z. So this cancels this. Taking the limits, we have minus 2z. So that is the partial derivative of u with respect to x, y, and z. Alright. We are looking at partial derivative by formula method. And we'll go back to function of one variable. If y is equal 3x cubed minus 2x squared plus x minus 4. Look at this, from function of one variable that we know. Okay, and we know that by formula method, dy dx will be equal 9x squared. That is using 3 to times this, we have 9. You reduce this by 1 minus 4x plus 1. Now this 4 is a constant, so it's 0 when we differentiate. That is a function of one variable. So we can also use this approach for function of several variables. For instance, let's just write back the function we just finished. F of x, y, z equal 2x squared minus xy minus z squared minus 5. So we want to find partial f. Okay, I think we're using u. We're using u of this. So partial u partial x is equal, if you differentiate this, you have 4x. Now we go to this term, that is x. Now in this term, I will do as if y is not there. See, I'm covering y because I'm dealing with only x. So y does not exist in that term. If I differentiate here by first principle, I mean by formula method, in calculus of one variable, if I differentiate this y, I mean this x, covering y like this, I will have minus 1. Now this term, there is no x, so I don't deal with that. Now if you compare this to what we had initially, you see that this is what we had initially when we were using first principle. Now let's also look at partial u, partial y for this function. So partial u, partial y, we are dealing with y. While we keep x and z constants. So there is no term here for y. But here there is y. So even when there is y here, we would now do as if x doesn't exist and differentiate only y. Of course, y is the variable there, so if we differentiate, give us 1. So 1 times minus x will give us minus x. There is no y here, so we leave that. And now see that this is what we got when we use first principle definition. We also go for partial u, partial z. This time, there is no z. There is no z. This is the only place we have z. So, if we differentiate it this time using formula method, I mean the method we know in calculus of one variable, you see that here will give us minus 2z. Yes, because we use 2 and times, we reduce this by 1. Now compare this with what we did in first principle definition. You see that we still have the same. So it's very simple to deal with. Very simple to deal with. Alright, so we are going to take some examples that will help us to see how we can evaluate partial derivatives. Now, if z is equal x squared y plus exponential 2y exponential 2y, or let's say exponential 2xy, this simple one, we are going to find partial z, partial y, partial z, partial x. If you are starting with x and with y anyway, so it's still the same. Find partial, okay, let me start with x. Find partial x, partial z, partial x, and partial z, partial y. Alright, so the solution will be in this way. We have z is equal x squared y plus exponential 2xy. Okay, here partial z, partial x. See, here I will assume there is no y, so it's only x that I see here. And that will give me 2x. So now I'm doing what? To add here. Plus. Now I want to differentiate here. We know that if I have exponential, for instance, I have exponential 2x in logarithmic calculus, that is y is equal to exponential 2x. If I want to differentiate it, I will have the y, the x is equal to exponential 2x. But this one is function of two variables. So, but it takes the same approach. What I'm going to do here, if I differentiate here with respect to x, I will have 2y. Because assuming there was no exponential, it was only this one. So if I differentiate with respect to x, I will have 2y. So I bring it down. Then exponential 2xy also exists. So this is how I'm going to differentiate with respect to x. If I also want to differentiate with respect to y, that is partial z, partial y. Now, it means that x squared does not exist. It's only here, y, but I see. So differentiating y, we have 1. So we have x squared plus, if I go here, I will have 2x exponential 2xy. So it's very simple to deal with. That is how we differentiate. Now we will now look at other examples. Let's look at these examples. Given the following functions, z is equal to tan 3x plus 4y, z is equal to 5x squared plus 2y raised to the power 4. Find partial z, partial y. Alright. Number 1, we have z is equal to tan 3x plus 4y. Okay, this is the same thing as writing to let u is equal to 3x plus 4y, so that z is equal tan u. Now, partial u partial x will be equal to 3. Partial z partial u is equal to set square u. Then we look at partial z partial x will be equal partial z partial u times partial u partial x, and this will be the same. Partial u partial z partial u is set square u times partial u partial x, which is 3. So we have 3 sec square u. But u is equal what? 3x plus 4y. Therefore, partial z partial x is equal 3 sec square 3x plus 4y. It's very simple to deal with. Now, see this thing there. The approach there is I'm differentiating here inside with respect to x, which is 3. And I bring the 3 out. Then I differentiate this one. When you differentiate time, it's set square. I times the 2 together. So it becomes very simple. Same thing will happen. Partial z partial y will be equal to differentiating out this one. With respect to y. So we'll have 4 set square 3x plus 4y. It's just very simple like that. Differentiate the inside out, and then you differentiate the function with respect to u, making it here u. So very, very simple. Now if I bring that approach to 2, I bring that approach to I, it means that z is equal 5x squared plus 2y raised to the power 4. Now, if we know chain rule in function of one variable, it can help us to understand it. Now, it means that partial z partial x will be, I'm going to differentiate inside here, just differentiate here out. Then I will use this power to times it and reduce this power by 1. Very simple. And so we have 10x, because if I differentiate inside here, it's 10x, so bring it out, times 4. Then we have 5x squared plus 2y reduced to 3. Now, times these two, we have 40x, and then we have 5x squared plus 2y raised to the power 3. That is partial z partial x. It's very simple to deal with. In the same way, if I need partial z partial y, it's for me to differentiate this inside. Of course, if I differentiate here, I have inside here with respect to y, I will have 2. Then carry the power and times here. Power is 4. Then fix the inside part. I will have x squared, 5x squared plus 2y raised to the power 3. So that this gives me 8 5x squared plus 2y raised to power 3. So that is partial z partial y. Very simple, very simple to deal with. Just differentiate the inside out, and then you keep the inner function, then you keep the outer function. If the function is in terms of trig that we have that time, differentiate that one too. If it is not, then just differentiate inside out, like we have to use the power and times it. Fix the inside back and reduce the power by 1. You can just get it right that way. Okay, so right now we are going to look at partial derivative of quotient function. What about if we have function in quotient form? How do we evaluate it? Very simple. The knowledge of calculus of one variable can help you to do that. Let's look at it. Alright, so we look at partial derivative of quotient functions. Now, if z is of the form z is equal f of xy over g of xy, then z is said to be in quotient form. The partial derivative of z with respect to x is the ordinary differentiation of z with respect to x, while y is kept, y is kept constant or is constant. The same rule for differentiation of quotient functions of one variable also applies. So even for y, that is partial derivative of z with respect to y, is the ordinary differentiation of z with respect to y. X is also gets constant. Alright. So if z is in this form, then z is said to be in quotient form. The partial derivative of z with respect to x is the ordinary differentiation of z with respect to x, while y is constant. Now the same rule for differentiation of quotient function of one variable, quotient function of one variable also applies. Now look at this. Partial z, partial x will be equal to g of xy partial f partial x minus f of xy partial g partial x over g of xy squared. So this is the definition of partial derivative of z with respect to x when they are in quotient form. The same thing will also applies if I need partial z partial y will be the same as g of xy partial f partial y minus f of xy partial g partial y over g of xy squared. So that is the definition. Now we'll look at the example so we know how to evaluate this. Given that z is equal cos 4x plus 2y over x squared y, find partial z partial x partial z partial y. Alright. By definition, we said that partial z partial x will be equal. Now, you know here g of xy, what it means is that g of xy, is it f of xy? F of xy is equal cos 4x plus 2y. That's what it means. And then g of xy is equal x squared y. So what I'm going to do now, we said that partial z partial x, that is partial z partial x will be equal g of xy. That is x squared. You know, okay, let me give the definition well so that it's clear. G of xy times partial f partial x minus f of xy times partial g partial x over g of xy squared. That is the definition. So now g of xy that we are keeping is the downside. So we can just see that partial z partial x is equal x squared y. I'm keeping x squared y. Then I differentiate f with respect to x. Okay, now if I differentiate this, I will have minus 4 sine 4x plus 2y. That is what I will have. Minus e of xy, which is cos. So cos 4x plus 2y times g of xy. That is differentiating g with respect to x times the partial derivative of g of xy. So that will give me 2xy. Alright. Then the downside is x squared y squared. So this can be evaluated to minus 4 x squared y sine 4x plus 2y. Then if we go this way, we have minus 2xy cos 4x plus 2y over the downside is x raised to the power 4y squared because of square here. So that is very simple one. Partial z partial y equal this. Also partial z partial x. So also partial z partial y will be equal the same definition. We have g of xy, then partial f partial y minus f of xy partial g partial y over g of xy squared. And if we do that, we know that this will be the same as keeping x squared y. We are keeping the downside here of xy. Then we differentiate f partially. This f, this is differentiate f partially with respect to y. And if you do that, you know, if you differentiate this with respect to y, you have minus 2 sine 4x plus 2y. You know, if you differentiate cos is sine. For elementary calculus, we know that you have done, they have offered the analytic calculus, and then you know all those things we are talking about. So it is assumed you know it. But if you know you have any problem that you don't know about analytic calculus, you can order for a package for that. We have it. You get the lecture well so that you can flow in what we are doing. So I'm keeping g of x y. I have to differentiate this. So I have minus 2 sine 4x plus 2y minus then f of xy is giving me cos 4x plus 2y, then differentiating the downside of half x squared over x squared y squared. So partial z, partial y will give me minus 2x squared y sine 4x plus 2y minus x squared cos 4x plus 2y over x raised to the power 4 y squared. So this is partial z, partial y. If you want to go further, then something is common here. We can factor it out and still write it, which means the same thing. So it's very simple to evaluate functions of several variables when they are in quotient form. Very simple. Look at that. Next, we look at partial derivative of product functions. Now, if z is equal f of xy times g of xy, if z is defined this one, then you know z is product function. Then partial z partial x will be equal f of xy times partial g partial x plus g of xy times partial f partial x. A product rule. That is the definition. So, same thing will happen. Partial z, partial y will be equal f of xy, partial g, partial y plus g of xy, partial f, partial y. If z is function of two variables, so this is 3 variables, 4 variables. We know the definition from our elementary calculus, so we apply the same. Now let's pick an example and see how we can evaluate it. Right. Example: if f of xy is equal to sine 3x plus y squared times 4x minus 3y, 5 partial f partial y. You know, here what we have, u is equal sine 3x plus y squared. V of xy is 4x minus 3y. So that partial u partial x is equal 3 cos 3x plus y squared. Then partial v partial x is equal 4. Alright. So partial u partial y is the same as 2y cos 3x plus y squared. Then partial v partial y is equal minus 3. So that partial f partial x, which is the same as writing u times partial v partial x plus v times partial u partial what x, will be equal u. Now u here is sine 3x plus y squared. That's for u. This is this. So times partial v partial x, which is 4. So plus v is 4x minus 3y times partial u partial what? X. Partial u partial x is 3 cos what? 3x plus y squared. So that is how the diminution is. And then this one will give us 4 sine 3x plus y squared. Okay, so if you use this and multiply this, we will have 12 plus 12x cos 3x plus y squared. Then if we go here, we have minus 9y, yes, cos 3x plus y squared. This is partial f, partial x. Okay, so now we have something common here. We want to factor it out. It's also correct to say y and 4 sine 3x plus y squared. Then we have plus 12x minus 9y is same with cos 3x plus y squared. So we just factor this. Right, so partial f partial x is equal this. Now I'd like you to find partial f partial y. Partial f partial y. You know, I've already looked at this. I've already differentiated this and that, this and this. So you look for partial f partial y. Now let me give you the view so that you get it quickly. That partial f partial y will be the same as u. We define it in terms of u. So just say u partial v partial y plus v partial u partial y. This is the derivation of that one. So keep u, also keep differentiate v with respect to y. Look at it. Then you also keep v. Then you times it with the differentiation of u with respect to y. So it's very simple. Alright. Now we will look at other examples. For this example, we want to look at if x is equal r cos theta, y is equal r sin theta. Prove that partial r partial x is equal partial x partial r. Then r times partial theta partial x is equal 1 over r partial x partial theta. Now let's pick the solution. We have that x is equal r cos theta, y is r sin theta, and we know that partial x partial r will be equal cos theta. So partial y partial r is equal sin theta. Also, partial x partial theta is equal minus r sin theta. Partial y partial theta is equal r cos theta. We differentiate y with respect to theta. Okay, so it's r cos theta. All right. Now, this is partial x partial r. So let's find partial r partial x. And so to get partial r, partial x, we express r in terms of x and y. We express r in terms of x and y. Now consider this plane. Consider the plane, the xy plane below. Now on this plane, if this is r, given the magnitude of r, we know that we can have that this side is y, this is y coordinates, and this one is x, so we have theta. Now what it means is that sine theta is equal, we know that it's opposite all over hypotenuse, which is y all over r, and so that implies that y is equal r sine theta that we had already. So that was how it was given, that y is equal r sine theta. Okay. Now see how where the thing originated. Also, cos theta is equal, cos is x all over r, which also implies that x is equal r cos theta. You see that? So remember that what we need is r. We want to express r in terms of x and y. And we know that by Pythagoras theorem, r squared will be equal x squared plus y squared. R squared, the hypotenuse, will be equal to x squared plus y squared. So if we have that, see we have got y. So that if we differentiate y partially, we have 2r. Of course, we differentiate this 2r. Partial r, partial x will be equal to x. This is not x, so we are differentiating it using implicit differentiation, implicit definition. So this also implies that partial r partial x is equal to x over 2r, which is x all over r. And don't forget that x all over r is equal cos theta. Look at it. So try to put it there for you to know. Okay, now we were to show that partial r partial x is the same with partial x partial r. Now look at partial x partial r cos theta. Look at also partial r partial x cos theta. Therefore, partial x partial r is equal partial r partial x, which is equal cos theta. So they are equal. Now the next one, we are asked to show that r times partial theta partial x is the same with partial x partial theta, and so we also need to define theta in terms of x and y. Now to do that, we also go back to our plane, to the coordinate plane. You see that theta, we know that tan theta is equal to y all over x. At this stage, it is assumed that the students should know this, that tan theta is opposite all over adjacent. Okay, is this. Now, if I want to differentiate this, if tan theta is equal to this, it means that theta is equal tan inverse of y all over x. That is theta. So I'm able to express theta now in terms of y and x. Okay, I want to differentiate it with respect to x and y. So let u is equal y all over x. See that? Which theta now will be tan inverse of u. That is how it will be. And so we know that partial u, partial x, partial u, partial x. What we need is partial theta, yes, partial x. So partial u, partial x, this is quotient that we just finished, will be x times differentiation of here, and there is no x there, so it becomes 0, minus, we keep y, differentiation of here is 1 over x squared. Now this will go, and we have minus y over x squared, yes, minus y over x squared. That is partial u, partial x. Then partial theta, partial u will be equal, if you differentiate theta with respect to u. In elementary calculus, we know that if y is equal to tan inverse of x, dy dx is 1 all over 1 plus x squared. So now that we have this theta with respect to tan inverse of u, so now write that partial theta partial u is 1 all over 1 plus what? U squared. Then we know that u is y over x. So we can write this, that it will be equal to 1 all over 1 plus y, yes, over x. X squared, yeah. It can be like this because u squared. Then what we need is partial theta, partial x. Partial theta, partial x, which you need from the question, will be the same as partial theta, partial u. No, yes, partial theta, partial u. Partial u times partial u, partial x. This times this cancel this, can give me back partial theta, partial x. And then what is partial theta, partial u? Look at it here. It become 1 all over 1 plus y squared over x squared times partial u, partial x, okay, partial u, partial x, is minus y over minus y. So let's take it up so that you understand. Minus y over x squared. Look at that. Look at that. And if we have something like this, what happens is that here we can take LCM for this one so that you can simplify it for this one. So if we take LCM for here, we have 1 all over x squared plus y squared over x squared. That is what it will be. And then times minus y over x squared. So how are we going to call this? By definition, we see that by multiplication, we see that this will be minus y over x squared plus y squared over what again? X squared times 1 all over x squared. You see that? So we mean that here can cancel here. And so what we have is y over x squared plus y squared. And this is the same thing as writing minus y all over r. Because r is x squared plus y squared minus y all over r. Minus y all over r. And this is the same thing as minus 1 all over r. Or can I write like this? 1 all over r. Yes, minus sine theta, no, y. Oh, no, minus, see, look at that, minus y all over r. You can write it as 1 over r minus r sine theta. Why? Because y is equal r sine theta. Yes, y is equal r sine theta. So if you don't have minus 1 over r and r sine theta, this define y. From here, define y. So this can cancel this, and I'll have minus sine what? Theta. Minus sine theta. Okay, that is partial theta, partial x. And we wanted to show that r times partial theta partial x is equal to 1 over r partial x partial what? Theta. Okay, now you see what we have. See what we have. What we have is r partial theta partial x, and we know that partial theta partial x is minus y over r. So only this one will give us r times minus y over r. That's what here gave us. Y here is giving us 1 over r partial x partial theta. So what is partial x partial theta? We can go back to our definition and look at partial x partial theta. We have partial x partial theta is minus r sine theta. Okay? So we also have minus r sine theta. Now look at this definition. That if you see what is here, also you also see what is here, because this place is the same with here. The definition of here become minus sine theta. Now look at, so the whole of this I can write minus, because this can cancel this. I can write minus sine theta. So this becomes minus sine theta. Now let's go this way. This can cancel this. We also have minus sine theta. Therefore, r partial theta partial x is equal 1 over r partial x partial theta. Okay, it's very, very good to know these definitions, how they are evaluated. You should also know that x is the same with r cos theta. Know that y is the same with r sin theta. So with this, we can put those values and get the exact value that we needed. So this is how it is done. It's very simple to follow. It's very simple. Next, we'll look at modulus function. Let z is equal f of xy. Z is said to be homogeneous function of degree n if the sum of the powers of the variable x and y at every term of z is equal to n. That is, if I have z defined as a function, and every term I add the powers of the variable x and y and give me n, that means the terms are equal. The powers, when I add them and everything, are equal. So such function is called homogeneous function. Now consider the function z is equal a sub the x raised to n plus a sub the 1 x raised to n minus 1 y plus a sub the 2 x raised to n minus 2 y squared plus a sub the n x raised to n minus n y raised to n. Now this function, I can write it in the form can write it in the form x raised to n. Then I have a from that a sub to o plus I have a sub to 1 x. I write y by x. You know how? Because this function means there is x down. So taking x up, it will turn to minus 1. It has a power minus 1 going to law of indices. So I'm bringing that x down and I factor out x minus x raised to n. So remain only y at the top plus a sub to 2. Then I have y over x squared plus a sub to n. Then I will have y over x raised to power n. Okay, so now this function, I can write this function in the form x sub to n 5 raised to y all over x. So z is equal to is homogeneous function. If the homogeneous function will be written in this form, this function will be written in this form. Now, this will take us to Euler's theorem. Euler's theorem on homogeneous. Function. Now, it states, this is that if z is equal x raised to n, 5 of 1 raised to x is homogeneous. Homogeneous function of degree n. Then x partial z partial x plus y partial z partial y will be equal mz. That is what the theorem states. That if z raised to n x raised to power n, 5 of y over x is homogeneous function of degree n. Then x partial z partial x plus y partial z partial y will be equal to nz. Now this theorem will soon be made known. It will be made clear when we take some examples. Let's look at the proof of this, whether it's true. Now z is equal x raised to n. Then we have 5 y raised to y over x. Okay. Partial z, partial x. If we differentiate this with respect to x, you see this product function. It's one function, x raised to is another. And we know our partial derivative of product is just length. So we can now see that this will be saying as x raised to power n. We just keep that and differentiate this. And if we differentiate this, we will have 5 prime of y all over x. Why we are doing that? If you recall when we differentiate theta with respect to tan inverse, you see, you differentiate tan, you also differentiate the other function, tan together. Then if I differentiate this y over x, of course it's clear that I will have minus y over x squared. If you know, we just say this differentiating this. So you should know, if you differentiate this by putting 2, you have minus y over x squared. Okay. So I get this and differentiate this plus keep this also. So if I keep this, I will have 5 all over x. Then I differentiate to have x raised to n minus 1. It means that I can write it in this form. Let me write it in this form. X n raised to n, x times x raised to n minus 1. That is this. 5 y of x minus, trying to bring this minus because the minus, if you cancel it, you have minus y, and then you have 5 prime of y x. Look at that. I'm going to take this up. Then I will have x raised to n minus. That is what I will have. I carry this one up. So you go to x's brother. So I have this. Now I'm going to multiply it through by x, so that we'll have x partial z x. Now the equal, if I use x to multiply this, here will go because our x will let this go. So we'll have x raised to n. Now we also have 5 y x. Then x times this minus y 5 prime of y all over x. Then we'll have x raised to n minus 1. Yes, that is what I will have here. By the time x is minus 1, we will find partial z partial y. We find partial z partial y. We will have x raised to the power n. Then we have 5 prime y over x. You know, we this and we differentiate this. And 1 over x. Of course, if it's differentiate this function only here. With respect to y, you have 1 over x. Okay. Plus, we also keep 5 of y over x. And we differentiate n. X is equal to y when you have 0. Because we don't have partial y is equal x raised to n. Then we have okay, x raised to n minus 1. I'm going to take this to n minus 1. Then I also have 5 prime of y over x. That is what it means. So if I multiply y, I have y partial partial y will equal y x raised to n minus 1, then 5 prime of y over x. Now look at this. From this equation, call it 1. Call this one 2. And the 2. That is adding 1 and 2. And we'll have x partial z partial x plus y partial z partial y, which is this side. I'm going to add this side too. Of course, if I add this particular term with this term, this particular term is almost good. So what I have here is n raised to n 5 y raised to x. Now we know z for 5 y over x for definition. So when we write this, partial z x plus y partial z partial y it is true. And that is the first theory. Now let's look at division application so that Euler's theory on homogeneous function f of x, y, z is equal 3x squared y z plus 5x y squared z plus 4z raised to power 4. So we will take the solution in this way. We have f of x, y, z equal this. Now partial f, partial x. You know that partial f, partial x is 6x y z plus 5y squared z. That is partial f, partial x. This time there is no x, so from here and here. Okay, now x, partial f, partial x. We use this sometimes here. We'll have 6x squared yz plus 5x y squared z. Okay, we also go for partial f, partial y, and that will give us 3x squared z plus 10x yz. Then y partial f partial y, that y times partial y, will give us 3x squared yz plus 10x y squared z. Okay. Also, partial f partial z is equal 3x squared y from here plus 5x y squared plus 16z raised to the power 3. This times this raised to the power 3. Okay. Then that is f, that is partial f partial z. Then z times partial f partial z will be equal 3x squared zy plus 5x zy squared plus 16 z raised to the power 4. Now we want to add x partial f partial x plus y partial f partial y plus z partial f partial z, which is this one, also this one, and then this three. So if you add that, we'll have, look at this term, we'll have this plus this will give us 9, and this will give us 9x squared yz. That's for this. Then if we go for this and this, we'll have plus 15xy squared z. Then we'll also go for here. We'll have plus 3x squared y plus 3, okay, look at plus 3x squared x squared yz, that is this one, plus 5x y squared z. Then we go for here, we'll have plus 16 z raised to the power 4. And that will give us this plus this, will give us 12x squared yz. Then this plus this can give us plus 20x y squared z. So we add this, we will have plus 3x squared yz. Okay, now this plus this, we have added that, and this is also added. So we have plus 16 z raised to the power 4. That is x partial f partial x plus y partial f partial y plus z partial f partial z. Now, what it means, what Euler's was trying to say is that if you are given this function, that it is that the partial derivative of f with respect to x, f with respect to y, f with respect to z, by multiplying x with this, y with this, z with this, will be the same as nz. That is, if you use the power and times the function, that it will give you the same thing. Now let's verify that here. We look at this homogeneous function and we see that here is power 2, here is power 1, here is 1. So we have power 4. Power 4. Remember the definition of homogeneous. We said that at every term the powers will be equal. So here is power 4, here is power 4, here is power 4. Now if I use 4 to times this particular function, it will give me exactly what I should get in going by this method. So now 4 f of x, y, z will be equal 4 times 3x squared y squared z, okay, yz plus 5x y squared z plus 4z raised to the power 4. Okay, now this times this will give me 12x squared yz. Then I will have 20x y squared z. Then I will have plus 16 z raised to the power 4. Now look at that. And that is the same as saying nz. This is nz. This is 4 times z. So you see that what we have here is the same thing that we have here. So that means if I'm asked, if I'm giving this function now, if I'm giving this function f of x, y, z is equal 3, 3x squared yz plus 5x y squared z plus 4z raised to the power 4. And I am asked to find, you see, find x partial f partial x plus y partial f partial y plus z partial f partial z. So the best thing I will do, provided this is homogeneous, is to know the n, that is the degree of this homogeneous function. Instead of doing this process, I can use n to times this function, just that. Then I will have the results. So that is Euler's theorem. It's very interesting. Now, the next subtopic we are looking at is total differentials. So let's z is equal f of x, y, f of x, y. Let's just do that. Let z is equal f of x, y. And let's change in z, change in x, and change in y be increments. The increments in z, x, and y respectively. Then we have z plus change in z will equal f equal x plus change in x. Then we also have y plus change in y. Now, increment is in all the variable. So if I subtract y from both sides, if I subtract y, I will have, if I subtract z from both sides, I have that z plus change in z minus z will be equal f of x plus change in x, then y plus change in y minus f of x y. Of course, z is equal f of xy. Alright, so it means that change in z will be equal f of x plus change in x, y plus change in y, minus f of x, y. Now here I'm going to add adding f of x, y plus change in y, adding this, and also subtracting. I will add and also subtract so that I can still get this. Of course, if I do that, I will have change in z is equal f of x plus change in x, y plus change in y, okay, minus f of x, y plus change in y. I'm adding and subtracting. That is what I'm doing. I add and also subtract. So subtracting, I'm adding this and subtracting also, so that there will not be anything. You know, if I add and subtract, I've not done anything to the problem there. I've not done anything to what is on the board. So I'm subtracting this. I'm going to also add. So, but let me have that change in x plus f of x, y plus change in y, minus f of xy. See what I'm trying to say? In this place, f of xy minus this. I'm subtracting and also adding. So if you add this to 9, it becomes 0. You get back this place. Okay, so now I can also write this to be f of x plus change in x, y plus change in y, minus x, y plus change in y. Then I have change in x over change in x. There's nothing wrong there, because if I cancel here back, I'll still get back here. Plus I have f x, y plus change in y, minus f of x, y. Then I have change in y over change in y. Look at that. So it still becomes the same, because this can cancel this. But there is what I want to use it for. That if I take limit, taking limit as change in x approaches 0, change in y approaches 0, we will have that the z will be equal partial z partial x dx plus partial z partial y dy. Now look at that. So now this is called total differential. This is the total differential. And suppose, okay, let's say if z is equal f of xy, and we have that x, we have x is equal phi 1 of x. We also have another one. We have x is equal phi 1 of x, y is equal phi 2 of x, y is equal phi 2 of x. It means that if I divide this into by the x, I will have that the z over the x. Okay, let's say x is equal phi 1 of t, and then y is equal phi 2 of t. Yeah, x and y, they are functions of t. So I will have that dt. If I divide through by dt, I will have that dt is equal partial z partial x dx dt, okay, plus partial z partial y dy, what, dt. Alright, now the z dt is called the total differential coefficient. This is the total differential coefficient. So this is what we call total derivative. The z is equal partial z partial s dx plus partial z partial y dy. So we'll look at some examples that will also let us understand what we are doing. Right. So given that z is equal u squared plus v squared and u is equal 80 squared, v is equal to 80, find the z dt. I've told us that this z dt is the total coefficients, is the total differential coefficients of z. Okay, so let's put the solution. We have z is equal u squared plus v squared. Now partial z partial u will be equal to u. Partial z partial v will be equal to v, which we know. Now u is equal 80 squared, and so du dt will be equal to 80. We also have that v is equal to 80, so that the v dt will be equal to a. Now what we need is the z over dt, and that will give us partial z partial u du dt plus partial z partial v dv dt. So that is the total differential coefficient of z, as the z dt, which we shall have it that will be equal to partial z partial u, and partial z partial u is 2u times the u dt. The u dt is 280 plus partial z partial v, which is 2v, times the v dt is 2a. So we have 480u plus 4av. Okay, but u is equal 80 squared and v is 280. So we can substitute that in this place so that we get it. In one variable. So the z dt. So we now have that the z dt will be equal 4a t. Then we have 80 squared, because u is 80 squared, plus 4a times 280. Okay, and so this will give us 4a squared t cubed plus 4a squared, 8, sorry, this time this is 8a squared t. Okay, and you can write this to be 4a squared t. Yeah, we bring 4a squared t, then we have t squared plus 2. Yeah, but because by the time we use this to times it, we have 8a squared t. Yeah, so we have it this, and that is the z dt. So it's very simple. It's very simple to follow. Now look at this definition from here, so that you have partial z partial u times partial v partial t times the u dt. The same thing applies to this place. So The next subtopic is chain rule. Now, if Z is equal f of u v w, where u is a function of sy, v is a function of sy, and w is a function of sy, then partial z partial x will be equal partial z partial u times partial u partial x plus partial z partial u partial z partial v times partial v partial x plus partial z partial w times partial w partial x. So that is the chain rule. And partial z partial y is the same as partial z partial u times partial u partial y plus partial z partial v times partial v partial y plus partial z partial w times partial w partial y. So this is chain rule. Now we will take example and see how we can apply the chain rule in partial differentiation. So example, if f of u v is equal to u squared minus 3u v plus v squared, and u is equal x squared minus y, v is equal x plus 3xy. I'm going to find partial f partial x and partial f partial y. Alright, we'll take the solution. F of u v is equal u squared minus 3ub plus v squared. U is x squared minus y, while v is equal x plus 3xy. Okay, so we know that partial f partial x is defined as partial f partial u times partial u partial x plus partial f partial v times partial v partial x. Yes, because we have two now. F is function of u and v. So now let's look at partial f partial u. Partial f partial u is equal to u minus 3v. Partial f partial v is equal minus 3u plus 2v. That is differentiating f with respect to u and with respect to v. Right, so partial u partial x, it will be equal to 2x. To differentiate this, u with respect to x is 2x. Then partial v partial x is the same as 1 plus 3y. Yes, 1 plus 3y. So partial f partial x will be equal partial f partial u which is 2u minus 3v times partial u partial x is 2x plus partial f partial v which is minus 3u plus 2v, then partial v partial x which is 1 plus 3y. Right, so that means this will be the same. If we use this to times this, we have 4xu minus 6xv plus, okay, this will be minus because of, we use this to times this, we have minus 3u plus 2v plus, okay, minus 9, that is this times this, minus 9yu. Then use this to times this, we have plus 6vy. Okay, so partial f, partial x. If we can change this to x and y, better. So we have x, then u is x squared. X squared minus y minus 6x. V is x plus 3xy minus 3u. U is x squared minus y, then plus 2v. V is x plus 3y. Then another one we have here is minus 9. That's minus 9y. We have u, which is x squared minus y plus 6v. V is x plus 3xy. Okay, and as y. You see, all the variables now have turned to x and y. So by evaluation of this, we'll have the function now in terms of x and y. So that is partial f, partial x. Okay, so this will give us 4x cubed minus 4xy, right, minus 6x squared minus 18xy, right, minus 3x squared plus 3y plus 2x plus 6xy minus 9x squared y plus 9y squared y squared. Then we also have here plus 6xy plus 18xy squared. That is partial f, partial x. Alright, so we have 4x cubed. Then for x cubed, we can write as x cubed. That is 4x cubed minus 3x cubed. Okay, we have another one, which is minus 4xy. Also have minus, okay, let's go for square, minus 6x squared. I think that is the only one that we have square for x. So this and this can give us minus 22xy. We have 6 here. Okay, so minus 22 plus 6xy. We also have another xy here. So we have 12xy minus 22xy. And that gives us minus 10xy. Because minus 22 plus 12. So xy has finished. Now, let's also go again for, we go again for minus x minus 9x squared y. Yes, this is the only x squared y we have. So we have minus 9x squared y. So we are done with this, I'm done with this here, and this one also. So the only one that remains is here. Then we have 9y squared, 18xy squared. Okay, there are different terms. So plus 9y squared plus 18xy squared plus 2x plus 3y. So this one is partial f, partial x. we can also define partial f, partial y. And we know that it will be partial f, partial u times partial u, partial y, plus partial f, partial v times partial v, partial y. So we need partial u, partial y. And we know that u is this. So partial u, partial y will be minus 1. Now, partial v, partial y will be 3x, because v is equal x plus 3xy. So partial v, partial y is 3x. Okay, so partial f, partial y will be equal partial f, partial u, which we have already done, to be 2u minus 3v times partial u, partial y, which is minus 1, plus partial f, partial v. Partial f, partial v is minus 3u plus 2v. Then we also have partial v, partial y, which is 3x. Okay, so we have minus 2u plus 3v minus 3xu plus 6xv. So that is partial f, partial y. So if we substitute u is equal x squared minus y, and then v is equal x plus 3xy, we can also get in this form. So that is how we define the chain rule, and it's very simple. Now I'd like you to substitute this. Substitute u is equal x squared minus y, and then v is equal x plus 3xy, so that you get it in this form. It's very simple to do. So the next topic we are going to look at is implicit function. Now, if w is an implicit function of x and y defined by the equation f of x, y, w equals 0, then partial w, partial x will be equal minus partial f, partial x divided by partial f, partial w. Similarly, partial w, partial y will be equal minus partial f, partial y divided by partial f, partial w, provided that partial f, partial w is not equal 0. Okay, so the proof. Let z is equal f of x, y, w. Now, by chain rule, we just need chain rule. So by chain rule, partial z, partial x is equal partial z, partial x times partial x plus partial z, partial y times partial y, partial x plus partial z, partial w times partial w, partial x. So by chain rule, we have this definition. Now, you see, this is the same thing as writing partial z partial partial x, because this partial can cancel themselves, so we have this plus partial z partial y times partial y partial x plus partial z partial w times partial w partial x. Now that is partial z partial x. Now if partial y, we are dealing with x now. So if partial y partial x becomes 0, and then we also have that partial z partial x becomes 0, but we want to deal with this. Okay, you know, I will use f. We are using f in the place of z this time. We are using f. So these are f. So that partial f partial x will also go to 0. Then what I will have here will be, I will have partial f partial x plus partial f partial w times partial w partial x, like that, equals 0. So that here partial w partial x will be equal minus partial f partial x divided by partial f partial w, which is the same thing that I wrote here, partial f partial x and partial f partial w. So that is for partial w partial x. That's what we have. Now for partial w partial y, we know that by definition of chain rule, let's look up for this. By definition of chain rule, from this function we will have partial f partial y will be equal partial f partial x times partial x partial y plus partial f partial y times partial y partial y plus partial f partial w times partial w partial y. Now if also we let partial f partial y become 0, and then we will have a partial x partial y is 0, because we don't need partial x partial y, yes, we don't talk of x this time, we are talking about y. That was why we let partial f partial x, partial y partial x becomes 0 in this one, because we are dealing with x. So if I do that, I will have partial f partial x times partial x partial y, though I will put 0, but I want to show the definition. This can cancel, so we have partial f partial y plus partial f partial w times partial w partial y. Okay, so now this is 0, and we know that we will let partial x partial y also become 0. So with that, we will have that partial f partial y, if this and this are 0, see the only thing that remains, plus partial f partial w times partial w partial y equals 0. Now transferring this, we will have that partial w partial y will be equal minus partial f partial y over partial f partial w. We are making this subject of the formula. So this is how we get partial w partial y. So by this way we have partial w partial y. Okay, now we are going to take example of this. so that we now understand the process of this chain rule very, very well. Let's take example. If x cubed exponential y plus z minus y sine x minus z was defined z as implicit function of x and y, find partial z, partial x, and partial z, partial y. So let's look at the solution. You know that x cubed exponential y plus z minus y sine x minus z. Okay, so now this function is in this way: f of x, y, z. You know that partial f, partial x will be equal partial f, partial x times partial x plus partial f, partial y times partial y, partial x plus partial f, partial z times partial z, then partial x. And what we need is partial z, partial x. And in this definition that we just finished, we know that we have partial f, partial x, because this can cancel this. So plus partial f, partial y times partial y, partial x plus partial f, partial z times partial z, partial x. So partial f, partial x is this. And if we let partial f, partial y, we don't need y in this context, it will be 0, and this is 0. So we will have partial f, partial x plus partial f, partial z times partial z, partial x equals 0. So that partial z, partial x that we need will become minus partial f, partial x divided by partial f, partial z. Okay, so this is partial z, partial x that we need. So an elimination there. And then we can now go to this function, and when we find partial f, partial x, what will be partial f, partial x, partial f, partial x. Look at this. Will give us x cubed. Then we have, okay, this is in this function here. This is function. It doesn't carry x, but it's a function of its own. So we have x cubed 0 plus exponential y plus z. Then we have 3x squared. Then we go to this term to also differentiate with respect to x. We have minus y cos x minus z. Yes, minus y cos x minus z plus, that is, I keep minus y, I differentiate this. Then I will also keep sine x minus z. If I differentiate this with respect to x, I have 0. So what I have there for partial f, partial x become 3x squared exponential y plus z minus y cos x minus z. Alright. Now, I will also look for partial f, partial z. Then that will give me partial f, partial z. Look at that. I think it's only here for differentiate. So that will give me minus y, keep minus y. That differentiate is to have cos x minus z. You know, I have x here. Okay, I will have yes, minus y. I will keep minus y and differentiate this, and this will give me minus 1. Then I keep back cos. So this is minus 1. This will give me minus, I have minus y minus cos x minus z. So I'm keeping y and differentiate this plus. I will keep sin x minus z, differentiate y to be 0. Then everything here give me y cos x minus z. That is for partial f partial z. So that partial z partial x that we need become minus partial f partial x over partial f partial z, and that will implies minus of this. That gives us minus 3x squared exponential y plus z plus y cos x minus z over downside is y cos x minus z. So this is partial z partial x. Bend this. So in the same way, we can also divide partial z partial y. So I'll leave that as an exercise. Partial z partial. So find partial z partial y from what we have learned. Find partial z partial y. Okay. So for you to find partial z partial y, take the division that partial z partial y, know that partial z partial y will be equal minus partial f partial y over partial f, yes, partial z. Yes, this is the definition, and then you find partial f partial y, just as here. Also find partial f partial z. We have this. Then later you can find partial f partial z, partial f partial z. But now partial f partial z, we have already got it to be y. Okay, we'll define here. Look at, okay, we didn't look at this thing. So plus 3x squared exponential y plus z. You know how? Because here, if you differentiate it with respect to z, z is 1, so it will still be the same thing. And so that means here will be 3x squared exponential y plus z. Yeah, plus this. So when you can now, what you only find now is partial f partial y, because the downside is still the same. That is this one. So I've already got here for you. And so what you will do is only to find partial f partial y. Now go to the function, this function, find partial f partial y only. So I should get partial f partial y. They divide it by partial f partial z, which is already here. And so the work is done. We are looking at implicit function using determinant approach. There is another approach, by determinant approach, you can use. Now suppose we have two functions. F1 of xy ub equals 0 and f2 xy ub equals 0. We have two functions now defined by this equation for u and v being implicit function of xy. Then we know that partial f partial x plus partial f1 partial u times partial u partial x plus partial f1 partial v times partial v partial x. Yes, this is the definition by chain rule. You know that this will be equal to 0. And then for f of f2 of xy uv, we can also define that this will be partial f2 partial x plus partial f2 partial u times partial u partial x plus partial f2 partial v times partial v partial x will be equal 0. Now this way, if we need partial u partial x and partial v partial x, okay, so partial u partial x and partial v partial x can be obtained by writing the equation in determinant form, or by evaluating this equation in determinant form. Okay, let's put that by evaluating the equation using the determinant approach. Thus, let's write this equation in this form. You know that if we transfer this to this side, we can have that partial f1 partial u times partial u partial x plus partial f1 partial v times partial v partial x will be equal minus partial f1 partial x, and also partial f2 partial u times partial u partial x plus partial f2 partial v times partial v partial x will equal minus partial f2 partial x. So we have two equations now, equation 1, equation 2. Okay, 1, this is 2. Now if you look at it very well, it resembles linear equation, which we can evaluate it by Cramer's rule. You know Cramer's rule very well, that we can use Cramer's rule to solve this equation. Now see how we are going to write it. In determinant form, we can in matrix form first. We can write it as matrix form as partial f1 partial u, yes, and then we have again partial f2 partial u. I'm taking this. We also have partial f1 partial v partial f1 partial f2 partial v. Then we are solving for partial partial u partial x and partial v partial x. So we are solving for this one will be equal to minus partial f1 partial x minus partial f2 partial x. So if you know determinants, matrix using Cramer's rule, you know that we can define this equation like this. And what we do now is to find the determinants of this. After getting the determinant of this particular one, then we can now remove this and substitute a constant there. Just the same thing with Cramer's rule. So that is what we are going to do. We define this for partial u, partial x, and partial u, partial y. The same thing will also be true if we need partial u, partial y, and partial v, partial y. So this is how we can do it. So if we put this in determinant form, we will have partial f1 partial u, partial f2 partial u, partial f1 partial v, partial f2 partial v. Now we can now evaluate this provided this determinant is not equal 0. It is not equal 0. Okay, provided it is not equal 0. So that then a similar definition, we can also define partial u, partial y, and partial v, partial y to be the same thing as partial f1 partial u1. We also have partial f1 partial v, partial f2 partial u, partial f2 partial v. Then we have partial u, partial y, partial v, partial y will be equal minus partial f1 partial x, partial f2, partial f1, yes, partial f1 partial y, partial f2 partial y. Okay, so that is another definition you can use to get these two. So that partial u, partial x, now see, partial u, partial x will be equal the determinants of partial f1 partial x. Then we also have partial f1 minus partial f1 partial x, yes, then minus partial f2 partial x, then partial f1 partial v, then we have partial f2 partial v divided by the determinants partial f1 partial u, and then partial f2 partial v, then partial f1 partial v partial f2 partial v. This is for partial u, partial x. That is, this is Cramer's rule. What we do here is to bring this one and fix it here. We remove this, divided by this original determinant, this one, which must not be equal to 0. Provided it's not equal to 0, we can evaluate this. Then the same thing will also happen for, look at partial v partial x. Partial v partial x will be the same as partial f1 partial u, partial f2 partial u. Then what we do here is to bring this one also, bring this one also and put it in this place C, so that we can also remove this one, so that we have minus partial f1 partial x minus partial f2 partial x divided by this same one, which is partial f1 partial u partial f2 partial u. Then we also have partial f1 partial v partial f2 partial v. This can become very simple for those who know grammar school, and grammar school at this stage, we believe we know it. So that's why. If you feel you don't know it very well, what you do is to get our lectures on linear algebra. There we treat a lot of things that involve matrices and other ones like dimension. There are many lectures there that you can get. So you get all the knowledge. But if you know this one, you know that it's very simple. By knowledge of grammar school, that you can solve it easily. So the same thing will also be true. We can find partial u, partial y, partial v, partial y. See this one here. So what we do in that one is to say partial u, partial y will be equal to, we also define these determinants by breaking this into here. Then you remove this, and we will have minus partial f1 partial y, okay, yes, minus partial f2 partial y. Then we have partial f1 partial v partial f2 partial v, this. So when you have that, we also divide it by original determinant, which is partial f1 over partial u, partial f2 partial u. Then we have partial f1 partial v, partial f2 partial v. So if you do this, you can also get this. Alright, then we'll also look for partial v partial y, which is the same thing as writing another determinant where you have partial f1 partial u partial f2 partial u. Then we bring this one also, which is this, and put it in this way where we have a v function, and that will give us partial, okay, that will have to give us minus partial f1 partial y minus partial f2 partial, okay, sorry, yes, partial y minus partial f1 partial y, then partial f2 partial y, divided by these determinants, this same determinant, partial f1 partial u, partial f1 partial v, partial f2 partial u, partial f2 partial v. Okay, so by doing that, we can now get partial u partial x, partial u partial y, partial u partial, then we also have partial v partial x and partial v partial y. Yet it's very simple to deal with. It's only if you don't understand basic mathematics that we learn. Maybe at your first year, you must know these words, those things that will help you understand this. So if you know you don't understand those concepts, now those lectures you can get them back by ordering for a package that contains lecture. You have it. Let's look at this example. If 3x plus y minus u squared plus v is equal to 0, and x minus 2y minus u plus 2v squared is equal to 0, define u and v as implicit function of y, of x and y. Now find partial u partial x, partial v partial x. Then partial u partial y, partial v partial y. Now see what we do. Now we know that f1 is equal, look at f1 is equal 3x plus y minus u squared plus v. Now f2 is x minus 2y minus u plus 2v squared. So you have two functions just as I showed you before. Now partial f1 partial x is equal 3. Partial f1 partial y is equal 1. Partial f1 partial u is equal minus 2u minus 2u. And so partial f1 partial v is what? 1. So we have done that. It's so simple like that. Just take each one in the functions for f1. Then we also have that partial f1 partial f2 partial x will be equal 1. Partial f2 partial y will equal minus 2. So partial f2 partial u is equal minus 1. Okay, partial f2 partial v is equal 4v. So immediately we get that, the next thing is to find partial u partial x. Then by definition we said that partial u partial x will be equal minus partial f1 partial x. Yes, partial f1 partial x, and partial minus partial f2 partial x, which we have put there. Then we also have partial f1 partial v partial f1 f2 partial v divided by partial f1 partial u partial f2 partial u partial f1 partial v partial f2 partial v. So now the first thing we'll do, let's put these functions, these things here. Now going by this way, we will have taking these determinants. We know that these determinants will give us partial f1 partial x. Now partial f1 partial x is 3. So we now have minus 3 in that place. Partial f2 partial x. Partial f2 partial x is 1. So we now have minus 1. So partial f1 partial v, partial f1 partial v is 1. Then partial, that is f2 partial v, partial f2 partial v is 4v. That is the up one, divided by another determinant, that which is here. Partial f1 partial u is what? Partial f1 partial u is minus 2u. Partial f2 partial u, partial f2 partial u is minus 1. Then partial f1 partial v is 1. Partial f2 partial v is 4v. So with that, you can evaluate this determinant. This times this gives us minus 12v plus 1 over. Then if you go with this, you have minus 8 uv, then plus 1, which is the same as partial u partial x is the same as 1 minus 12v over 1 minus 8 uv. So that is partial u partial x. Now in the same way, partial u partial v partial x will be the same as, we are going to remove this partial, okay, this is partial v partial x. We are going to remove this one and also bring this to here, and we define it, that is here, partial v partial x. We define it to be partial f1 partial u, partial f1 partial f2 partial u. Then we put minus of the other. So partial f1 partial u partial f1 partial u give us minus 2u. Partial f2 partial u give us minus 1. And then this place can bring this to become minus 3 and minus 1 divided by 1 minus 8 uv. You know, 1 minus 8 uv is still the same determinant. And if we evaluate this, we have 2u minus 3. So divided by 1 minus 8 uv. That is partial v, partial x. So it's very simple to evaluate. We also look at partial u, partial y. Let me take it. Now, partial u, partial y. We define it to be minus partial f1 partial y. Then we also have partial f1 partial v, and then minus partial f2 partial y, and partial f2 partial v, divided by, we'll divide it by this because it's the same function, divided by 1 minus 8 uv. Okay, so this will give us determinants. We have minus partial f1 partial y. You see, partial f1 partial y is minus 2u. So we have minus 2u. Now, partial f2 partial y, partial f2 partial y is giving us minus 2. Okay, partial f1 partial v is giving us 1. Partial f2 partial v is 4v divided by 1 minus 8 uv. So this time this can give us minus 8 uv, and then this time this can give us plus 2. You know how we take determinants? It's 2 by 2 matrix. We take determinants. So it is assumed that you have offered those basic lectures, and then you should know them. Now I divide here by 1 minus 8 uv, which is the same thing as having that partial y, partial u, partial y is the same as 2 minus 8 uv divided by 1 minus 8 uv. So that is partial u, partial y. Then partial v, partial y is the same as partial f1 partial u partial f2 partial u. They have minus partial f1 partial y minus partial f2 partial y. Okay, divided by the same determinant, which is 1 minus 8 uv. So with that we will have that partial f1 partial u, which we have already got in partial f1 partial u, partial f1 partial u is minus 2u. So we have minus 2u. Then partial f2 partial u is giving us minus 1. Then what we'll do is partial minus. Okay, we have minus partial f1. Okay, now look at it. We have something here, minus partial f1 partial y. Partial f1 partial y is minus 2u. minus 2u. So because of the minus that is here, so here will be plus. So we have got it. Here will be plus. And when we come to partial f2 partial y, partial f2 partial y is minus 2. So because of the minus that is already there, so here will be plus. And that is how this times this will become a. Okay, will become 8uv minus 2. Correct. Minus 2. Very good. 8uv minus 2. That is what we have here. 8uv minus 2. So now in this case we have partial f1 partial u. Partial f1 partial u is minus 2u. Partial f2 partial u is minus 1. So partial f1 partial y, for our definition, partial f1 partial y is 1. So this minus will make it minus 1. Partial f2 partial y is minus 2. So with this minus we have 2. Okay, then this divided by 1 minus 8uv. And then if we evaluate these determinants, we evaluate it, we have minus 4u minus 1. You know, this time this is plus, but the invisible minus that exists when we take determinants of 2 by 2. So over 1 minus 8uv. So that's become partial v partial y. Okay, so that is how we can evaluate implicit function using determinant approach.